Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next episode in the Coding Geometry Dash in Java series. If you remember from the last episode what we got to, or we actually just did theory. So we did the theory behind some triangle collision detection. And then in this episode what we're going to do is we're going to actually code that triangle collision detection using the Cohen Sutherland algorithm and rotating points about origins. So those two algorithms that we sort of went over in that theory is what we're going to be doing today. So there's nothing really new in this episode. It's just going to be going over what we went over in the theory. The only hard, difficult spots that we might encounter are the implementation of Cohen Sutherland's algorithm. It's a little bit weird because it is recursive in functionality the way I coded it, because it was the easiest way to enable the clipping and then run another test. You could do a loop too, which we will examine a little bit, and I'll explain where you could change it to a loop if you want to. But for mine, I did it recursively, and there were a few bugs when I was doing this, so I had to do a lot of debugging, which I'll show you a little bit of how you could do if you want to debug yourself, if you're doing this yourself and you have some problems or something and you're trying to figure out what's going wrong. So we'll look at all of that in this episode and see how to do all this. Like I was saying earlier, we got to a point where we can trigger the broad phase collision detection, and we now know how to do the full-on narrow phase collision detection, which is what we're going to be implementing in this video. Since we have all that theory, one of the first things I mentioned in the theory was rotating points about an origin. So that's going to be the first thing that we're going to calculate in this video, is rotating points about an origin. So we will create a private, it will return a vector 2, and this is just going to be called rotate point. And it's going to take in the angle in radians, the vector 2, the point we want to rotate, and a vector 2, the origin we want to rotate around. So if you remember, I said we need the cosine and the sine of the angle. So we'll say math dot cosine of the angle, and double sine equals math dot sine of the angle. And this angle is in radians. That is important to remember. Next thing we're going to do is we're going to create a new vector, and this will be basically the vector that has been rotated around the point. So we'll say it's a new vector 2, and we're just going to pass it p.x and p.y. So we're just going to initialize this at the same point that the original vector is at, and I got to change that to vector 2. Next thing we're going to do is we're going to subtract the origin, which is exactly what we want to do. So we'll say subtract o.x and subtract o.y, because we have to subtract the origin before we can actually rotate the point to make sure it's rotating about the origin. And then we'll add in the origin once we return the vector. Next, we'll say the new x equals, and this is literally just the equation that I wrote out inside of that theory video. So it's just new vector dot x times cosine minus new vector dot y times sine. And then our new y is just new vector dot x times sine plus new vector dot y times cosine. And that will give us exactly what we need. And then we just need to return a new vector 2, and we'll give it the new x plus the origins x, and the new y plus the origins y. And that will officially rotate our point correctly. Now let's go to our calculate transform. Right now we're not taking rotation into account. In the future we will be able to rotate our triangles and any blocks that we want. So let's add in functionality that will calculate the transform with the rotation embedded into that. So we'll take in the angle in radians, our angle, which will be math to radians, gameObject.transform.rotation. So this will be the angle in radians, and then we'll say vector to p1 equals a new vector 2, and this is going to be basically just all of this stuff. So we'll copy all this into actual vectors, and then I'm going to copy this one for the y, and I'm going to do that for 3 vectors. So I'm going to fast forward real quick and finish that up. Now that that's all done, we're just going to rotate each of these vectors. So we'll say p1 equals rotate point, and we'll take in the angle in radians, p1, and the origin, which we also don't have yet. So what is the origin? Well, the origin is just the center of this block, right? How do we get to the center of the block? Well, we can just add in the game objects transform x plus half a tile width and the y plus half a tile width. So let's do that real quick. We'll just say the origin equals a new vector 2. And then we'll take in this guy's transform position x plus half of a tile width, which we can get right here. And then for the y, we'll take in the game object's transforms position dot y plus half a tile height, which we can also get through this simple equation. There we go. Okay, so now we have the origin, and then we'll just do the same thing for P2 and P3. So we'll rotate it about the radian angle, and then we will about the origin too. So, and then one more time, our angle, P3, and origin. Next, we just assign all these values to the appropriate vectors or variables. So this dot x1 dot y1 equals p1 dot y, p1 dot x, and then so on and so forth. And that should be good. So now we have our transform officially calculated correctly, taking into account any angles that our player may be at. Now, how do we test this to make sure that this is all working correctly? We want some way to like check and see if this is actually going to work. So let's go up here right before we calculate the transform. Let's set our GameObject.transform.rotation to 90 degrees. This way we can see if we actually are doing this right. So the triangle should be rotated 90 degrees to the right. And then let's implement our draw method so that we have something to draw this with. So this will take in graphics 2D. And this is basically just debugging visually, because we could do the numbers and look at the numbers and see if they're right, but this is a little bit easier because we can easily see, okay, that looks right. So what we're going to do is we're just going to say, draw some lines. So we'll say g2.draw a new line 2d.float, and we will take in this dot x1, this dot x2, or this dot y1, sorry, this dot x2, and this dot y2. And then I'm just going to copy this and change this one to x3 and y3. And then just change this to x3 and y3. Doesn't matter which direction we're drawing these in, this will work no matter what. And I'm going to set the color to color.green. And if we look onto our triangles here, they should all be rotated 90 degrees. And as you can see, that's working perfectly fine. Let's try 45 degrees just to make sure that it is working with not just simple angles like that. So 45, we should see them calculated at like an angle to the slightly to the right. And that's what we get. So that's good. Let's delete this now. I forgot to delete that and was wondering why the heck my game wasn't working right. Comment this out, just Control/ for comments. And then we will move on to the next portion, which is actually implementing the narrow phase algorithm. So let's go up to our narrow phase, and we're actually going to start filling this thing out. We're going to need a few different things. So we're going to need P1, which is just a new vector 2, x1 and y1. We're going to need P2 and P3 also vectors, just like we've been doing. And you may be like, why do we have these stored as points and not just vectors if we're going to be transforming them back into vectors all the time? That's because we do use them as points in other portions of the code where it's easier. So it's nice to just have them as both and just transform them when we need to. Okay. The origin is the center of the box bounds. So let's get the center of that bounds. So we'll say vector 2 origin equals new vector 2, and we'll take the B1 game object transform position x plus, and then we'll do bounds dot width, or B1 dot width, I'm sorry, over 2.0 f, and then we will take in B1 dot game object dot transform dot position dot y plus, and we'll do the b1 dot height over 2.0 f. So now we have the origin that we will be rotating these points around, because remember we have to rotate these so that they are on the same axis as the bounds. Next is the angle we will be rotating these points at, which is, so we'll say angle, well, I'll call this R angle because this is the angle in radians as well. Float math to radians, and we're going to take b1.gameObject.transform.rotation. So we're just going to rotate it so that it's on the same rotation as the box bounds. So next we're going to rotate the points about the center. So P1 equals rotate point, and then we're just going to say angle, P1, origin. And this is our angle, not just angle. Do the same thing for P2 and P3. And then this is the part where we actually implement that Cohen Sutherland line algorithm. How do we know if we're intersecting now? Well, now we can officially use these points since they are on the same axes as the player and check and see if the player is intersecting with any of the lines. So the lines would be P1 to P2, P1 to P3, and P2 to P3. So let's implement an algorithm that checks and sees if a box is intersecting with a line. So we will go private boolean box intersecting line, which will take in a point. So vector 2, P1, vector 2, P2, which are just the 2 points that represent the endpoints of the line. And then it will take in a depth because, like I said, this is recursive in nature. And we do want to bail if it starts going too far into depth, which it never should. But just in case, it's good to have those catches. And then we'll take in a bounds and we will take in a position. And this is running just a little bit off the edge, so I'm going to take that down. So using all these different things for our intersection tests, we can actually write our Cohen Sutherland line algorithm. So I'm going to just comment at the top that this is actually what this thing is, and it's not line, it's the clipping algorithm. I'm sorry. I said the completely wrong algorithm in the last video. After when I was looking up, I was like, this is not the right algorithm. And then I realized what it was, and I got the two confused from my graphics class. But this is the right algorithm. So first thing we're going to say is if depth is greater than 5, first of all, we do want to know about this because if it's bailing, it shouldn't be. We'll say max depth exceeded. So this will clue us off, hey, something might be wrong. And then we'll just return true. We're going to assume that it is colliding if we have exceeded that max depth. I guess you could assume that you're not colliding, but when I've done the tests, typically if it exceeds the max depth, it is colliding and something's just going wrong. Next thing we're going to need is some way to compute region codes. If you remember, each portion of our little box and clipping space has a region code. Let's write a function to do that because it'll be much easier. So we'll go right down here. We'll say private int compute region code. And this will take in a vector 2, the point, and it will take in a box bounds, the bounds. We're also going to need some values for what represents like the inside, the top, the left, and the bottom, all those different things. So let's go up to the top of our file, and then we're going to say inside is 0, just like we did. And then we're going to, and we can make these all integers too. There's nothing wrong with that because the computer will do binary operations once we use the correct operators, which I'll show you as well. Left is going to be equal to 2, or actually 1, and then final int right is equal to 2, private final int bottom is equal to 4, and private final int top is equal to 8. In binary, this is just 0, 0, 0, 0, this one is just 0, 0, 0, 1, and this one is just 0, 0, 1, 0, this one is just 0, 1, 0, 0, and lastly, we have 1, 0, 0, 0. So you can see we have each of our columns filled with one number, which is exactly what we want. You could do these in any order as long as the inside is 0. Do these ones in any order, and it doesn't matter. This algorithm will still work correctly. So let's go back to our computing of the region code. How do we know what region we're in? Well, we know that if we're to the left of the box, then we should OR our value with the left and so on and so forth. So we'll start off. We're going to assume it's inside. We'll say the int code equals inside. And then next, we're going to get the top left of the bounds. So we're going to say top left equals bounds.gameObject.transform.position. And then we're going to say check if the point is to the left or right of the bounds. And if it's not, then it will remain inside because we won't do anything to it. And so the code will just be inside. So we say if the point.x is less than top left.x, I'm just going to change this p to a point, a little bit more explicit, a little bit better. Then we know that the code has to be ORed with the left. And this one pipe, this is the logical OR operator in Java. And then we'll say else if point.x, and this left should be all capitalized as well. If the point's x is greater than the top left's x plus the bounds.width, then we know that it's on the right. And since we know it can't be on the left and the right, we only have to do that once. But next we have to check if the point is above or below the box. So we need a separate if else if statement for this because it could be above or below and to the left and to the right. We don't know that. So we'll say if point.y is less than top left.y, then it is above. So we'll say code or equals top. And then we'll say else if the point.y is greater than the top left.y plus the bounds.height, then the code should be ORed with the bottom. And then this will return us the appropriate code. So this is exactly how Cohen Sutherland's algorithm says to compute the region code. You just OR it with the appropriate sides for the regions it's in. So now that we know how to compute the region code, let's actually compute the region code and store that for our use. So we'll say code 1, which corresponds to point 1, P1, is compute region code for P1 and the bounds. Then we'll say int code 2 equals compute the region code for P2 and those same bounds. Next, we want to check and see if the line is completely inside or outside or half in and half out, which we can tell with these two codes alone. So we can say if code 1 equals 0 and code 2 equals 0, then we know it's completely inside. Line is completely inside, return true. It is definitely intersecting with that line. Else if we can say code 1 and code 2, you do a single and for a logical and operator, does not equal 0. So if it's not 0, then we know that the line is completely outside, as we saw from our theory video, and then we can return false. This line is definitely not intersecting. Else if code 1 equals 0 or code 2 equals 0. So we know that they're not the same because this one would tell us if they were the same. If they were the same, then it would definitely equal 0. But if code 1 is 0 or code 2 is 0, then we know that one point is inside, one point is outside, so it's definitely intersecting. And then I'm going to leave a comment there just so that you can tell in the future. So we definitely know that it is intersecting. What if it's not? Then we have to clip it and rerun the algorithm one more time. So we need a couple variables, xmax equals int position.x plus bounds.width, where position is, if we remember going up here, where this position we will be passing in is just the position of this box bound. So we didn't very explicitly state that, but that is exactly what it is. And then we're going to say xmin equals int position.x. So we have the minimum x and the maximum x of our little box. Next, we need a couple other variables to compute the slope of the line. So if you remember, m, which is slope, is just y2 minus y1, or p2.y minus p1.y, over x2 minus x1, or p2.x minus p1.x. Then we can calculate b by using either one of the points. I just used p2, so we'll say p2.y minus m times p2.x is what b is. So now we have the slope of the line, we have the intersect of the line, so we have y equals mx plus b, the whole equation for the line. I'm just going to move that up there just to remind ourselves why we calculated those values. Then what we're going to be doing is actually computing where to clip it. So we can say if code 1 and left equals left. What this says is if the point is on the left side. That's basically what this is doing. Because if code 1 and left equals left, then that means we have it on the left side, because that one would be checked off in at least one of the columns no matter what region you're on the left side. If the code 1 is on the left, then first of all, we're going to add 1 to ensure we're inside the clipping polygon. Next, what we're going to do is we're going to say p1.x equals xmin plus 1. So that's the plus 1. To ensure that we're inside, we're just going to add one more to push us a little bit further along that line slope. That way, when we're checking the region codes, we are fine just using these less than, strictly greater than operators. Next, what we do is we calculate the y. Well, y is just mx plus b, or m times p1.x plus b. Simple, right? It's just super simple. So we clipped it. Otherwise, if it's on the right, code 1 and right equals the right. If we are on the right side, then subtract 1, first of all, not subtract 1 for the same reason. And we'll say p1.x equals x max minus 1. Notice we're on the right side, so we use x max. We're on the left side, so we use x min. That's for a reason. Next, what we do is P1, or this is, yep, P1 dot y equals m times P1 dot x plus b. We could just move this out, take this away, because all we're doing is changing the x in these. So we change the x and then we calculate what the final y would be depending on which x we have. Now repeat for the P2, for the point 2. And I spelled repeat wrong twice. I don't know what is up with that. Okay, so we're literally going to do these exact same thing. I'm just going to fast forward real quick. Alright, so what we did was we just did the same exact thing except for code 2 and P2 instead of code 1 and P1. We just said if it's the left, we do x min. If it's the right, we do x max, and then we calculate the y for that point. Next, like I keep saying, this function is recursive. So we've clipped the polygon. Now, how do we know what we do next? Well, we just return box intersecting line, and we use P1 and P2, the now clipped points. They have now been clipped. They're different. Depth plus 1, since we are going down a level, the same bounds, the same position. And this will officially continue to recurse and clip until we are fully aware of where we are and we know, hey, this is definitely colliding or this is definitely not. In reality, this should only ever go down 2 layers. This should only run twice at most, because if we clip it once, then we are now at a position where we can tell whether it is intersecting or not. In actuality, there may be some sort of bug where it doesn't and we would hit this. And if that does occur, if you see this popping up for whatever reason, then you go in, you start debugging, and you try and figure it out. This is why I have this here. I actually did run into this problem and then realized that I had a problem when I was calculating this value right here. I was using p2.y here instead of x and had a really major bug. So keep this line of code in here. It helps you out. Now let's go back up to the end of our narrow phase. Now that we have a way to tell if a box is intersecting with a line, we can literally just say return box intersecting line P1 and P2, and the depth would be 0. Now let's bring this up. The bounds, we have the bounds as B1. Position we have as b1.gameObject.transform.position. And then we'd say or box intersecting line P1 and P3, depth would be 0. B1, actually let's do P2, P3. I'm not completely sure how I had these, but I'm just going to do exactly what I did in my test code. b1.gameObject.transform.position, or is the box intersecting with the line P3 to P1 with a depth of 0, b1.gameObject.transform.position. So we just say, okay, is the box intersecting with the line P1 to P2, P2 to P3, or P3 to P1? If it's intersecting with any of these lines, this is why we have the ORs, then we have triggered a narrow phase collision detection. So we just return this. That should be it. That should be our narrow phase collision detection completely done. Let's test it. Let's see if this works. So we'll go into our code, and we have a couple of things here. Before we do this though, there is one last thing that we need to do, and that is kill the player if he collides with the triangle. So we can go into our bounds class. This is actually pretty simple. We know that if this triggers, so if it triggers the check collision, then it's going to go into here. And we can literally just say if b.type equals bounds type dot triangle, then we'll just say player.getComponent, player.class dot die. So if it collides with the triangle, all triangles are deadly, we'll just kill the player. Simple. It's nice, okay? Now let's test it. We'll hit F3, I saved that little scene that I made, and I die when I hit the player, and I die when I hit the player, and if you notice, if I jump like right in between this little gap, you will notice that it waits till I get into that gap before it actually triggers it, which means that we have some pretty good collision detection going now. Let's go back into the triangle bounds real quick. And let's remove this printing broad phase collision. And then let's go into the let's go into the player component class actually, because first I do want to fix some things. It's weird whenever you die, it doesn't reset properly. So we'll change the reset to work a little bit better. So this is the current die method. Instead of going to 030, let's go to 500, 350, which is what the player actually starts at. And this will just make sure that it goes better. And then let's also say GameObject.getComponent, rigidBody.class velocity.y equals 0. And this will just ensure that if the player is in the middle of a jump, he won't continue to jump after he dies and is respawned. And we'll just say GameObject.transform.rotation equals 0, resetting the transform. That way, when we play it now, it will all look right and the camera will just continue moving. Now, if you notice, this jump is currently impossible, even though it's possible in Geometry Dash. This is not an error with our collision detection. This is just because of the way the boundaries are working in some of our physics settings and everything. So what I'm going to do is I'm going to go into our level editor scene or our level scene. And then I'm just going to, first of all, remove, we have two of these, 2 box bounds. Remove that one. We definitely don't need that. We just need one. That must have been an oversight with me. And then next what we're going to do is we are going to reduce his bounds just a little bit. We're going to say -2 and -2. Give us a little bit of leeway with pixels just to be tolerant for the player, which is what people usually do. They make the box bounds of their player. Actually, what they usually do is they make the box bounds of the player a little bit bigger and then of the triangles a little bit smaller, which we may do in a future video too, because as you can see, this is still really annoying. But it is possible. I've done it once. Let's do another test real quick, because one of the main tests that we had was, can the player go underneath them without dying? And then I'm just going to put like 1, 2, 3, and then 1, 2, 3. And we'll do like a spike at the end of this one. So save that real quick. Player goes underneath perfectly fine, and everything else is working perfectly fine. So as you can see, we're getting really close to being completely done with this game. I hope you guys like this. If you did, please hit like and subscribe to stay tuned for the upcoming tutorials. Don't forget to hit that bell, and I will see you in the next tutorial. Thanks. See you.